This short video will cover the addition reactions of alkenes. This first reaction shows that you've got your alkene molecule reacting with hydrogen gas. This does require a platinum catalyst, and the double bond breaks, which leaves you with this single bond here, and two hydrogen atoms add on, one to each of the carbons. So the alkene has become an alkane. This is an addition reaction because it involves the breaking of the double bond. Some people also call this hydrogenation, but you don't need to. The second reaction is this one here, where you're reacting bromine water. Now, you do need to know that bromine water is like an orangey brown colour. When it reacts with the alkene, again the double bond breaks and one bromine adds to each of the carbons. Very important that you don't put both bromines onto one carbon. That is an error and will be marked wrong. There is a colour change that you need to know for this reaction. What will happen is the orange-brown solution, that's the bromine water, when added to your alkene, which will be colourless, when you add those two together, it will decolorise. And that reaction is rapid and does not require any catalysts, does not require UV light. It will happen in the dark, that colourless change. So yes, definitely know that. It's how we can test for the presence of a double bond. This next reaction involves, again, addition reaction. Instead of it being Br2, we use hydrogen bromide. So what's going to happen in this situation, again, double bond breaks. On one carbon, a hydrogen will add on, and on the other carbon, a bromine. So you do form a haloalkane, but just one bromine atom goes in this instance due to the reagent being HBr. Notice if we just flick back quickly, when the reagent was bromine, water, Br2, you got the two bromines. So this is a haloalkane. This would be 1,2-dibromoethane. This is also a haloalkane, but it's just 1-bromoethane. This next reaction, again, it's an addition reaction. It involves the addition of water. Now, it does need to be acidified, so that's like a catalyst. What you sometimes will see is the formula written H2O/H+. You don't need to write this full word on top of your arrow. Okay, so /H+ is sufficient. So again, the double bond will break, and what will happen in this instance is one of the hydrogens from the water will add to one carbon, and the OH group, which we refer to as a hydroxyl group, adds to the other carbon. So your alkene has become an alcohol. The other reaction of alkenes is polymerization. So you'll need to have quite a few of these alkenes, so we refer to these as monomers. Okay, so you can see up here the word monomer. So again, the double bond breaks and it will add on to the adjacent monomer. The again double bond breaks, which will add on to the adjacent monomer. So what you end up with is this long string of carbons, and depending what groups are added to the double bond, this instance it will be just hydrogens, but you might find that there could be a chlorine or a methyl group. So to name a polymer, you put the word poly in front of the monomer name. So this is polyethene. Even though there's no double bonds, you still keep the ene. Okay, so that's worth noting. Now, sometimes we have asymmetric alkenes, and we need to be careful because you'll get two potential products in this instance. What is an asymmetric alkene? What you want to do is look at where the double bond is here. Focus on one carbon at a time. You can see that this carbon on the left has two hydrogens, and the carbon here on the right also has two hydrogens. So when the number of hydrogens is the same, we would term this symmetric. When you've got a alkene, and you look at the left carbon and it's got 1 hydrogen, and the right carbon has got a different number, in this instance 2, when the number of hydrogens is different, that is when we call it asymmetric. So here what you'll see, this carbon's got 1H, this carbon's got 1H also, same number, symmetric. This carbon has 1 while this carbon has 2, different number, asymmetric. Again, carbon has 2, carbon has 1, different number, asymmetric. So that's how you determine whether something, a alkene, is symmetric or asymmetric. Now, if you do have an asymmetric alkene undergoing addition, we need to use Markovnikov's rule, and you do need to be able to quote this rule, not word for word, but you need the idea. So the carbon atom that is in the double bond with the most hydrogen atoms is more likely to get the hydrogen atom from this reagent, while the carbon with fewer hydrogens will get the non-hydrogen atom. In this instance, the non-hydrogens are bromine. Now, some people learn the rule rich gets richer, which would mean that this carbon here with the 2 hydrogens would gain the next hydrogen. Never write rich gets richer to explain this rule. You'll get marked not achieve. So in order to identify the major product, this shows you that the carbon with the most hydrogens has gained the extra hydrogen, while the other carbon with the fewer has gained the non-hydrogen, in this case the bromine atom. So this is the major product. So 2-bromopropane is the major product, while the alternative, so this is where it hasn't followed Markovnikov's rule, this is the minor product. So 1-bromopropane is the minor product. Here's just another example. So you identify which carbon's got the most hydrogens. In this case, it's this carbon here on the left with 2, and it will gain the hydrogen for the major product, while the non-hydrogen, so that's the chlorine, will go to the other. So that's the major product. So 2-chlorobutane here is the major product, while the alternative arrangement with the hydrogen going to the carbon with the fewest and the chlorine going to the carbon with the most, this is then the minor product. So that is when you've got hydrogen chloride. Notice you don't need Markovnikov if this was chlorine, so Cl2, because they'd both be chlorines. One other example, and you'll see here I've got that H+, which is, instead of writing the word sulfuric acid, so again the double bond will break. This carbon's got 2 H's, so that's why it's got the hydrogen atom gone on there, while the other carbon on the left here has only got 1 hydrogen, and so that's why it's got the OH. So this has made an alcohol. It isn't ethene 2-ol because there are 3 carbons in the longest chain. You do need to keep your eye on the fact that that carbon chain includes this group up the top. This is not a methyl group. You cannot get side chains, methyl side chains, on terminal carbons, which is a word we use for the end carbons. Terminal means the end, whether it's at the beginning or the end, does not matter. Okay, and then there's your minor product. So just to reinforce this idea where students remember rich gets richer, it's definitely a great way to remember the rule, but you should never use it in your exam. Instead, you need to explain it by using this statement here. The hydrogen atom from, now it might not be HBr, it could be HCl or H2O like we just looked at, but the hydrogen will bond to the carbon in the double bond that has the most hydrogen atoms already bonded to it. If you can write that statement in red, that will get you excellence. Now, one last thing I'll cover quickly in this video is how do you remember all these reactions? In organic chemistry, we use reaction maps. So this is a very, it's actually probably half of the level 2 reaction map. This shows you all the reactions in one little diagram. So in the center here, you've got your alkene. It shows that if you're adding hydrogen with your platinum catalyst, you get an alkane. If you add bromine water, you get your haloalkane. If you undergo polymerization, you make a polymer. If you add water, you make an alcohol. And if you add HBr or HCl, then you'll get a haloalkane. So the X here represents a halogen atom. In a later video, I'll cover this reaction here. The reason it's different with the red arrow and not the blue is it's not an addition reaction, it's an oxidation reaction. It does involve the double bond breaking, but two OH groups add on. And we'll talk about these black arrows in later videos. Those are elimination reactions. So if you can remember these blue ones at the moment, you've made a really good head start into knowing all the reactions. This here is the same diagram, but it shows, instead of the names of those homologous groups, the functional groups. So all single bonds, it's got the halogens, and you can see here what I'm talking about is the diol. That's our representation for a polymer. This here represents an alcohol, and that there represents the haloalkane. So I hope you found this video useful. Thanks.